Students, I'm sorry I wasn't in school last Friday. I must have sprained an angle. Get it? Alright. So this next proof is a little bit more complicated than the one we just did. Rather than being about proving two triangles are congruent, right, we're instead trying to prove that two line segments are congruent. AB and BC. But we know, because we know the MO for proving that line segments are congruent, that the way we are probably going to do that is by finding two congruent triangles and then looking at their corresponding sides. So, alright. We actually have three triangles in this picture if you count the big one. But I would like to focus your attention on Reddy and Bluey, my two friends here. Reddy, also known as triangle BDC, and Bluey, also known as triangle BAD. It is bad to the bone. So we have triangle BAD, and we have triangle BCD. And you know what? I suspect that those triangles are congruent. I have no evidence for that as of yet, but I think it's true, and I bet we'll find that evidence later. But for now, here's the important thing. CB and AB are corresponding sides of those triangles. So if we were able to figure out that those two triangles are congruent, that in fact Reddy and Bluey are equal to one another, then on that basis we would have the evidence to finish this proof. We would have the evidence to say that AB is congruent to BC because corresponding parts of congruent triangles are congruent, because CP, CT, C. Well, that's all very well and good, you may say, but just where, pray tell, where are we actually going to find the evidence that these two triangles are congruent? Well, says I, just look at the givens. Alright, what do we have? BD bisects angle ABC. Alright, well, angle ABC is here, okay? BD is this line here. So if BD bisects angle ABC, I know one half of it must be here, and the other half of it must be here, right? The two halves of angle ABC. Okay, those are congruent. What else? Well, I know that BC is perpendicular to AC. And if they're perpendicular, I have, hello. I have some 90-degree angles, which I will attempt to draw. Whoa, box. There we go. Nice. 90 degrees all around. Okay. So as I'm thinking through my triangle congruence options again, right? I have my Fab 5. I have SAS. I have SSS. I have ASA. I have AAS. And I have HL. Well, right away, HL kind of jumps out at me because I have right triangles, and I know I need to have right triangles to use HL, but the more I start thinking about it, the more I feel like HL is not going to work. There's a couple reasons why I'm thinking that. One is that one of the other things here that I know is an angle, and you know that's not really going to help me do HL. Right, hypotenuse and leg, it's both line segments. But the bigger reason is that, look, what's our goal again? We're trying to prove that CB and AB are congruent by CPCTC. And you know what those sides are? That's right. It's the hypotenuse. So if I'm trying to prove that the hypotenuses are equal, I can't really use the fact that the hypotenuses are equal as evidence. That doesn't really make any sense. So I think I'm going to exclude HL. But what else do I have? Well, I have two angles, okay? So that rules out SSS and SAS. It's going to be one of these two. It's going to be either ASA or AAS, and for both of these I need at least one side. And fortunately, you know what? I have good old BD, which is congruent to itself by the reflexive property. And BD is right in between these two pairs of angles. So ASA it is. All right. Now I'm ready to turn this into a proof. So again, to recap my strategy, I'm getting 1A from the fact that BD is perpendicular to AC, right? So I'll have to explain what that means is that these angles here are 90 degrees and all 90-degree angles are congruent. Okay. My S is BD being congruent to itself. That's a reflexive, that's a reflexive property argument. And then finally, that these two angles are equal to each other because I know BD is the angle bisector of ABC, and the definition of angle bisector cuts it in half, and the two halves are equal. So my last is coming from the angle bisector there. Okay, so now that I've brainstormed, let's write this up into a jolly proof. So here we go. Start with the givens I'm going to use here. BD bisects angle ABC. Again, I can't get all the notation right on the computer, but just know that if you were doing this for real and not for play, you would want to have the little line segment. Ooh, that's a terrible line segment. You would want to have a little line segment hat there and a little angle there. Okay. The reason for that is that it's given. And I might as well go ahead and explain what that means right now before I get to the other given. So the fact that BD bisects angle ABC, right? I'm going to claim that angle CBD is congruent to angle ABC, right? I just named these two angles that I marked in red here, CBD and, oh, ABC, no, sorry, DBA, there we go, DBA, there we go. And the reason for that is the definition of an angle bisector. All right, now I'm ready for my second given. BD is perpendicular to AC. That is given. Now what does that mean? Well, it means that angle BDC is right and angle BDA is right. We have a right angle on both sides here. That is the definition of perpendicular. Now, all right angles are congruent. And if this were HL, I wouldn't need to include this step because I'm not directly comparing the right angles. I'm just using the fact that it's a right triangle. But because I'm using ASA and I'm treating this as just any old A, I should mention that fact. So I'll say angle BDC is congruent to angle BDA because all right angles are congruent. All right. All right, my whatchamacallit, my brainstorming seems to have vanished here, but that's okay. I'm almost done. We're now going to say BD is equal to itself by the reflexive property. And now, okay, we have our pair of angles, and our side in the middle. So we are ready to say triangle BDC is congruent to triangle, BDA by the ASA triangle congruence theorem. And finally, now that we know that bluey and reddy are congruent, now that we know that triangle BDC and triangle BDA are congruent, we can also, conclude that because of that, their two sides here are congruent. BA and BC must also be congruent because corresponding parts of congruent triangles are congruent, also known as CPCTC. And I actually am going to name it AB and CB just to match the prove statement that we have up here. And that shows me very clearly, because this matches my prove statement, that we are Dunsville.